In this video, we are going to go through reactions of alkenes. Specifically, we are going to study what we will do to a particular double bond when we see a particular reagent. We will do more of mechanisms since there are other videos that we are going to do specifically mechanisms, but for now we are going to look at what we will do to a double bond when we see a particular reagent. Now let's take this first reaction. We are having an H2 in the presence of palladium or a platinum, or it can be a nickel. When we see a double bond, what are we going to do to it? We are going to add two hydrogens. That's, we add the first hydrogen to form the other a carbocation, then we also add the second hydrogen. So what we have to know is that when we see this particular reagent, we are going to add two hydrogens. Now we also have this reagent also. When we see an HX, where the X can be any halogen that we are having. It can be a chlorine, it can be a bromine, or it can be an iodine. When we see any of these halogens, we just add the hydrogen plus the halogen. So that's what we are having here. We are going to go through some examples. Also, when it comes to a triple bond, we will talk about it later, but I would like to enlighten us on it too. Here we are having the gas, the H2, but here we are having two of the H2, meaning we are going to produce four hydrogens rather. We are going to add four hydrogens to a triple bond, of which we'll do it in our subsequent videos. Now, we also have addition of the H and an X here, where we add H and an X two times to a triple bond in order to form an alkene. So let's go back to what we are having with an HX. Now, before we can add any HX to a particular double bond, we need to understand Markovnikov regiochemistry. It states that when we have an unsymmetrical alkene, in other words, an alkene which is not symmetrical, we add, and then we have to add an H and then an X. What we have to do is that we add the X to the parts, which is less substituted, or the part which contains a higher number of hydrogens, in order for a carbocation to form on the other side of it. Now, the carbocation must be stable, and then when we talk about stable carbocations, we know a tertiary carbocation is more stable than a secondary carbocation, and then a secondary carbocation is also stable than a primary carbocation. So a tertiary carbocation is stable than a secondary carbocation, and a secondary carbocation is stable than a primary carbocation. Okay, so this can form, H can be added to the first, let's name here to be the first and then the second carbon. H can be added to the first carbon for the carbocation to form at the second carbon, or H can be added to the second carbon for the carbocation to be formed at the first carbon. Now when we look at these two compounds, this carbocation is more stable since it is a tertiary carbocation. It's more stable than a secondary carbocation. So Markovnikov rule states that then the tertiary one will favor the reaction. Therefore, when the H comes on one side on the first carbon, then the X, which is the halogen, will also form on the second carbon. Now we move on to the next reaction that we are having on board. We have the hydration of alkenes. Hydration of alkenes, all that you need to know is that when we are having a particular reagent and we talk about hydration, we are adding water. In other words, we are adding H and then OH to the two carbons which are forming the double bond. So where would the H go? Where would the OH go? That one also, some of them follows Markovnikov, others are also anti-Markovnikov. Now let's come to the first reaction that we are having here. When we are having H plus in the presence of water, we are going to add an H and then an OH. That's hydration. So we add one H to, say these are the two carbons. We add one H to one side, then we add OH to the other side. But before the OH comes, mostly a carbocation is formed at the stable side. Before the OH comes, meaning we are going to add the H and then OH, but carbocation forms on the stable side before the OH comes in. And take note, when it comes to this first reaction, there can be a carbocation rearrangement. How? When it comes to this reaction, carbocation rearrangement can be in the sense that when we have a particular reaction, like when we have a reaction of this with, say, this, we first add our hydrogen to this compound, we get something of this sort. Hydrogen comes, then a carbocation is formed here. But let's take note, there can be a carbocation rearrangement. That's how I was, just as I was saying, there can be a carbocation rearrangement, of which it can be one, a hydride shift. That's a movement of hydrogen. We are going to move hydrogen to replace a carbocation. They will change their positions. Or there can be an alkyl shift. An alkyl shift is when we have a CH3 moving to swap with the carbocation. So over here we can see there is a secondary carbocation. There can be a hydride shift between this particular CH3. This and this can shift to form this particular intermediate, where the CH3 will now come here. Then from there the halogen will come, from there the OH will come inside. So there can be rearrangement in this. So the OH comes like that. There can be rearrangement in this particular reaction. Let's take note of it. Now let's continue. So we also have mercuric acetate in water and then sodium borohydride. This is mercuric acetate. And then in this reaction there is also addition, in this reaction there is also addition of H and then OH here. This is called the oxymercuration demercuration. Here the first thing that occurs is the addition of the mercuric acetate. When we add the mercuric acetate to the double bond, say we have this double bond, mercuric acetate first come in for a carbocation to form. Mostly where we add the mercuric acetate will first be added, but mostly it forms a bridge, an intermediate bridge, where the OH later comes in. Then the mercuric acetate will be replaced with a hydrogen by the help of the sodium borohydride. So in this reaction, let's take note to this reaction, there is no carbocation rearrangement, so it's fixed. The H comes to one side of the carbon, then OH will go to the other side. There are examples in the subsequent videos, so don't worry about it. Now we go to the next reagent. The next reagent is called the hydroboration. This also, let's take note very carefully, this also adds a hydrogen and then an oxygen. But over here what happens is that the hydrogen and the oxygen that is added in an anti-Marconical form, meaning it doesn't follow Marconical rule, which states that the hydrogen should be added to the less substituted side for the carbocation to be formed at the more substituted side, so that the X will come over there. This one is the vice versa, it doesn't follow it. But yes, it also adds the hydrogen and then an OH to a double bond that we are having. The next is halohydrins. Halohydrins are also formed over a double bond when we have a halogen and then water. Halogen in the presence of water. When we have a halogen in the presence of water, a halogen and then an OH, that's why it's called halohydrin. So we are going to add a halogen and an OH to a double bond. So what happens is that halogen and then an OH is added to this double bond, and then mostly it is added in an anti-addition form. This is due to the fact that mostly with the reaction, what happens is the halogen forms a bridge. It mostly forms a bridge. Then when it forms the bridge, the OH comes from the other side. It's either from the back or it comes from the forward, and then takes one side of takes one carbon with the double bond. It comes in from that side, so it's either it comes from up or comes from down, then it forms the anti-addition. Let's take note. But the most important thing is that it forms the halohydrin. It adds the halogen and then the OH. Also, we also have HOX, where the X can be any halogen in the presence of the NBS or and water, or it can be water and then DMSO. That's a dimethyl sulfoxide. Now it also add an X and then OH, similar to the first one. It also added to a double bond, just like that. Okay. Now the next reaction that we are going to also look at is dihalocarbenes. Dihalocarbenes. When you see a reagent like a chloroform, when you're having a chloroform in the presence of potassium hydroxide, or a CHCl3 in the presence of a KOH, what happens is that there is a formation. There is first an intermediate form. That intermediate is the dihalocarbene. This intermediate that forms, and then this one mostly leads to the formation of this cyclo, a dihalocyclopropane. So we have these two halogens that is formed on this particular halogen. So these are the two carbons containing the double bond, then it forms over it like that. Now we also have another one over here, a diiodomethane. A diiodomethane in the presence of zinc copper in ether. It's called the Simon-Smith reaction. In this one, there is also a formation of a cyclopropane. So we have this C and then the C, then a cyclopropane will be formed. So let's take note of these two reactions also. Now, the next that we are having is the oxidation of the alkenes. Oxidation of alkenes. When we have, there are a lot of reactions that leads to oxidation of alkenes, meaning addition of oxygen or the removal of hydrogen from alkene. Now, when we have KMnO4 in OH or in the presence of water, in other words, this is mostly called the alkaline potassium permanganate. This is the alkaline, meaning in the base. It mostly forms a diol, similar to OSO4 in the presence of NaHSO3 H2O. These two reagents mostly form a diol. But let's take note with the osmium 4 oxide and then the KMnO4. KMnO4 in the presence of acid that's something else, but when it's in the base, it just reacts just as an osmium will do. So it forms a diol, and then the diol, they are on the same side, so you can either represent it by a dash like this, or you can represent it as a wedge. Here. So what we have to know is that it has two OH forming a diol or a glycol on the same side. Now, this that we are having is oxidation, the same oxidation of alkene, but this particular one, it leads to formation of say aldehydes or ketones and then carboxylic acids. Now, this is called ozonolysis. Ozonolysis. We are having oxone in the presence of zinc and then an acid. What happens is that there is an oxidative cleavage. There is a cleavage here, break in the bond. So carbon here, it breaks here. So it breaks like this. Then oxygen fill this place. So this is how it forms simply. So this is how it forms. We are going to do some examples of these reactions, then you are going to see. But what you have to take note of is that whenever you see oxone or ozonolysis, this reaction is called ozonolysis. When you see oxone in the presence of zinc in an acid, it's a mild oxidant mostly. It's a mild oxidant, so it just cleaves, breaks the double bond, and fixes oxygen at the two ends of double bond. Okay, we also have KMnO4 again. KMnO4 now in an acid is called acidic potassium permanganate. Now over here we can see we have a terminal alkene here, and then we have an internal alkene here. It does the same thing. When KMnO4 is in an acid, it works just like an ozonolysis, or it works just as an oxone would do. So it breaks it. Let's take this one first. So it breaks it like this: C double bond R R. It breaks it like this. With the internal one, it breaks it like this, then fix the oxygen there. So we can see that we are having a diketone. We are having two ketones here. So this can help us in synthesizing a lot of derivatives of carbonyls. Now, apart from this, when it is a terminal one, when it's a terminal and then it's not di-substituted, you see here it's not di-substituted, one is H and then one is R. It also breaks it just as it does to this one. Then it changes the H to OH. So it adds O to the H like this, and at the same time fix the O here. Plus it also fixed the O on the other carbon over here, but since it's terminal, it forms a carbon dioxide. It forms a carbon dioxide when it's terminal. So a carbon dioxide on one side and another side. So we can see a carboxylic acid being formed and then carbon dioxide being also formed. Now, the next and the last one that we are having on the reactions of the alkenes is the addition of halogens. So we are adding two halogens to a particular alkene. What happens is that these two also occur just as we added the two hydrogens, but the two hydrogens mostly on the same side. But this, it happens on different sides, or it happens in an anti-addition form. Now we are going to add an X and then another X also to the double bond. So if this is the double bond, we are going to add an X and then another X. So what we have to take note is that in this reaction we are going to add 2X to a double bond. So we add 2X to the double bond. Now over here, when it's triple bond, we will need 2 of the halogen, so that the first one, when we add it to it, it forms an alkene. Then we add the next 2 to it, then it forms a simple alkene where we are having X, 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 X like this. Thank you very much for watching.